Good morning, friends, or good afternoon, or good evening, whatever it is where you are. Couple of quick things here as we get going into week 11. PLC 11s, we'll get moving on that this week, and that'll be for Friday. And homework 5, finally, I didn't realize that it hadn't posted, as Canvas is making you play the game of check every small little tiny box that you can't find. Anyways, I got that going. We'll go for Thursday of next week, which happens to be the time of Celebration 2. That means that we will be talking about a finishing up of the thermo stuff this week, possibly into Tuesday of next week, but we'll cut that off and look at Celebration 2 coming on Thursday, 1 week on Thursday. All right. That means we'll go from everything we started with at started talking about thermo laws 0, 1, 2, and 3 right after the end of our optics section, all the way up to whatever we finish with, likely either Thursday this week, like I said, possibly Tuesday. So we'll see how we do, and we'll get moving to finishing this off, and then we are into modern physics and some special relativity, which could be our next topic. So with that, what we were talking about last time is the equivalence of the Clausius and the Carnot statements of the second law. And I had showed that the Carnot statement was equivalent to the Clausius statement. I just want to take a minute to show the other, well, I should say I showed it for one particular aspect of it. I want to take 1 minute to show for one aspect of it the opposite equivalence of Clausius and Carnot. Okay. Prior to starting this, I think what would be useful is to set out what is actually allowed by the second law or by the statements of the second law, because not a whole lot is. I thought it would be a good allowed. I'll just say allowed. I thought it'd be a good thing to just review or kind of present what these are based on what the statements are. Now, remember that in order to draw these things out, what we need is to examine the wording and to then set up something that obeys the wording. Now, both of these talk about heat reservoirs, so that's what these boxes are. These are heat reservoirs at different temperatures. I know I've talked about heat reservoirs before. The idea of these is that they are so large that a heat exchange with something else does not affect their temperature. In other words, if I take a glass of boiling water and I throw it in the ocean's temperature basically doesn't change. Therefore, the ocean can be thought of as a reservoir, and that's the thinking behind these two things here. Okay, this is a reservoir which is hot, and this is a reservoir, and this is the reservoir which is the cold. It's at the cold temperature, this is at the hot temperature. Therefore, what Carnot allows is a cycle. Okay, remember I'm just denoting the cycle process with the circle here. The Carnot process allows work to come out from a cycle as long as you exchange heat with no fewer than 2 heat reservoirs. And that means that we have to think about heat getting drawn from here. Since it's heat coming out of the hot reservoir, that is Q with the hot. We're then going to take some of that, transfer it into work, and then dump the rest. The rest gets dumped into here. This is called the cold reservoir, so that heat transfer is known as the cold heat transfer. And what we have is work which comes out. So this is a process by which heat can be transferred into work. And this is known as a heat engine. The basics of this we will be studying in a little bit more detail, possibly later today or in this video or a bit tomorrow. This is a heat engine. It is one way in which heat transfers into work. Another allowed way in which heat and work get transferred is the refrigerator. And that looks basically exactly like this, but everything's flipped. That means that I'm going to have a hot, a cold, and the heat getting dumped into the hot reservoir is still known as QH. This is still known as QC, but now in order to effect that transfer, work needs to be put into the cycle in order to cause the heat to come away from the cold and get dumped into the hot. This maintains the cold temperature by exhausting some of the heat into the surroundings and making the surroundings warmer, all right? This would be a totally allowed, this is perfectly well allowed as long as you're putting work into it. What's not allowed by Clausius is the situation in which you don't have the work put in. This is not an allowed situation according to the Clausius statement. So what I would like to do is show you how, if I deny the possibility of this, then I'm going to end up denying the possibility of this. And what I did in the last video or class was to do the opposite, which was show you that if I denied that I had to exchange heat with with two or more, if I could exchange heat with fewer than two reservoirs and get work out, then I could make the situation like this happen, which means that the Clausius statement is violated and therefore the Carnot situation is violated. So I just thought I'd do the opposite in this one and finish that off. So basically what this looks like is the situation in which I'm going to assume that this is okay. Let's assume that I can do something like that, right? And let's see where that takes us. So let's see. That's allowed. Let's prove. Okay, so I'm now going to prove. Okay, so now you've got that. What I'm going to do is I'm going to cheat and just erase this. But you should probably just draw it again, or not, whatever you like. We're just going to take this thing and go into a quick proof of how this melds with that. So what I'd like to do is add this. Right? This is not allowed. This violates the Clausius second law. So I'm using the contrapositive type of reasoning here. Right? So I'm going to take something which is incorrect and assume for a minute it's okay. What does it give me? The idea is it gives me something that is also incorrect because this is. Right? So what I'm going to do is I'm going to take this and I'm going to add it to a heat engine, which is totally allowed, do a few quick cycle adjustments, and check out and see what happens. Right? So I'm going to add this to a heat engine. Like so. Right? This is forbidden by the Clausius statement. This is an allowed Carnot heat engine, or it's allowed by the Carnot statement. It's an allowed heat engine. So if I set this and I add it to this, I'm going to get what? Well, now I'm going to make a quick cycle adjustment here. I'm going to adjust this heat that leaves the cold reservoir and this heat that is going back into the cold reservoir to be equal. And therefore the cold reservoir net loses and gains no heat. All right? When I do that, QH and QH will be opposite one another. but not equal. And I get a little bit of work out. So you'll see what ultimately is happening here is that if I call these, for example, primed quantities, like so, I'm going to set this equal to the situation of QC equal to QC prime. These two are going to add to 0. QH, I'm just going to assume that QH prime is greater than QH. I'm going to get W prime out, and you'll notice that my cold reservoir down here is just sitting here with nothing to do. Now, my proof goes as follows. If I assume that this is true, which we know it is not, and I utilize one of these in conjunction with this, what I can get to have happen is this. Stepping back, but wait a minute, I know this is incorrect. This is the violation of the Clausius second law. Therefore, this is a violation also, and it turns out it's a violation of the Carnot second law, because I am now exchanging heat with fewer than 2 heat reservoirs. I am putting heat into this thing and changing it completely into work. That's impossible, according to what Carnot's statement is. Therefore, at least with this simple example, I'm going to generalize and say these two basically tell us the same thing. Now, if you look back at the wording, remember the wording is very different. Clausius' statement is all about forbidding this process. Carnot is all about forbidding that process. They seem very different, but in fact, at their roots, they are saying the same thing. They are equivalent statements. Okay, so I'm going to leave it at that, and we'll go and explore a few more consequences of the second law statements that were made. Now, a couple of the things, well, actually, you know what? I want to leave that. I want to actually go in and look at this for a sec. So I'm going to put this back. QC, and then I had a reservoir here. What I'd like to do is just look at some of the properties of the heat engine itself. Cycle. Okay. And maybe I'll get to the refrigerator later, but this is not true, and therefore that's not true. All right, I want to take a look at this. This is your run-of-the-mill heat engine cycle. The idea is that whatever goes on here, if you have an ideal gas, you could imagine plotting it on a PV graph and saying, okay, the gas started here, did this, took heat in, did some work, exhausted heat, did a little bit of less work, and it comes back to the same place on the PV graph, and that's how this cycle works. What we're doing is we're dumping heat in, taking some work out, and dumping the rest of the heat. And what the second law of Carnot basically says is that you must always exhaust some heat. There is no way to 100% change a heat into a work. We cannot do that at an efficiency of 100%. That is what Carnot's, it's a consequence of Carnot's theorem. So let me cite for you a couple of theorems about the operation of heat engines. And I'm going to do this without proving it because we don't really have time and it's not really important for the benefit of the class here. So I'm just going to tell you a couple of things. I'm going to introduce a couple of also some other terminology in here. Actually, I think maybe we've talked about it before, but not extensively. The first thing is that a reversible set of processes. If I'm thinking about what this cycle is, right? Well, what's this cycle? Well, we know what the cycle is, right? We've already studied PV graph processes, right? Especially with the ideal gas. It could be a situation where we're going up and then we're going across and then we're going down and we're coming back, right? And we're doing some cycle where I started here and I'm coming back to here, and therefore this is the net work done, is the shaded area under the graph here. That's the work done by the process, or by the cycle. That's what's going on with this circle right here. okay? These things here are just there to remind you, hey, I've got to transfer heat in and I've got to transfer heat out. Now, one of the theorems that we run into here is that there's no more efficient way to do this than with what's called a reversible cycle. All right. So in other words, when I think about how to cause these processes to happen, I'm going to do them in a reversible way. All right. What does that mean? What that means is that I'm doing them so slowly that if I undid them, I would recover the original state that I was at before I did it. And I'm going to do that for every single step, every single point going from, for example, here to here, and ultimately all the way around. So if I'm, I don't know, consider this to be something like an isothermal, all right? Maybe it's a little steep for that, but whatever. Maybe this is isothermal. Okay, so what am I going to do? I'm going to put in a little bit of heat and allow it to do a little bit of work. No, I'm going to do a little bit of work and allow it to, I'm going to do a little bit of work and allow it to give me a little bit of heat out, right? So I'm going to compress it very slightly, and then I'm going to find out that there's a little bit of heat coming out, and I'll draw the heat out of it. Okay, and then I'm going to compress it a little bit again and let the heat come out. I'm going to compress it again and let the heat out. In other words, it's going to take me 50 years to go from here to there. Okay, and then it's going to take me another 50 years to go from here to here. I'm doing it so slowly that if I decided to, no, wait, I did that wrong, I'm going to undo this, the heat would come back in and I would recover the original state. That's what a reversible process is. At every point, I have taken very much care to make sure that whatever I do can be undone completely. Okay? Why are we interested in stuff like that? Because that gives us the absolute best possible situation. You can't do better than this. Nothing in nature is reversible, mostly, right? There's not a whole lot in nature that's reversible. So if you consider, right, I must not be having any friction between, if I'm doing this with a piston and a cylinder, right? There's basically no friction between the piston and the cylinder walls. I'm doing it so slowly that there's no turbulence involved in the gas, that there's no sudden heat transfers that are not going to be able to be reproduced the other way, right? So this idea of reversibility gives us the ceiling on how well we can possibly expect to do. All right, so our three theorems here is that there's no way to do better than a reversible process, right? So no heat engine that is operating between these two temperatures is going to be better than a reversible one. What this does is it establishes the reversibility as the best possible case. Right? Therefore, if we calculate the efficiency of the reversible cycle, then any other efficiency of a real engine will be less than that. Right? So that's the first one. The second one, which I'll write over here, is that if I have a reversible engine, a reversible cycle engine, then any reversible cycle engine operating between these two temperatures will have the exact same efficiency. Which is pretty cool because that means that they're all basically giving you the same thing. So all reversible engines operating between TH and TC, like this, and all reversible cycles, I really should say, operating between these two temperatures, whatever they are, they will all have identical efficiencies, right? They have the same efficiency. So for however much heat you're putting into this, it will give you the same fraction of work out no matter what the process is, as long as it's reversible. And the last one here is that the efficiency, okay, imagine that we have gone into this regime of, I've got a reversible engine here, and it's doing the best possible thing that it can do. The efficiency of that engine will decrease as the heat, as the temperature of this heat reservoir increases. The efficiency of the engine decreases. The efficiency is dropping as this temperature is moving closer to this hotter temperature, right, as it gets up. So the more of a difference between these temperatures you can have, the better the efficiency is going to be. And the closer that these things are, the less your efficiency is going to be. Now, an interesting historical perspective to this, I don't want to call them the Volkswagen people, but effectively, from the standpoint of the United States in the 1960s, cars were great. You could put these big, huge motors in the cars, and they made a lot of noise, and you could hot rod around, and you burn a lot of gasoline, but that was okay because it was basically free at that point, and nobody cared, and it wasn't doing any harm to anything. Come to find out later, in fact, there is slightly a problem with the amount of gasoline. In the early 1970s, there was a gasoline crisis. And we laugh about what happened today, but the prices effectively for that period skyrocketed. People were paying horrendously terrible amounts of money for a gallon of gasoline, like almost $1 per gallon. It was terrible. So the United States cars tanked because they were big, they were loud, they were noisy, but the worst thing that they were is inefficient. They were inefficient. And so when the Volkswagen Beetle got introduced to this country, it became a huge success. Why? Because it was an air-cooled engine. Now, yes, it was only a 4-cylinder compared to a lot of the V8s that America had in those days, and still does, basically. So partly that was a step in the right direction, but the engine itself was cooled by air and not by water, which meant that it had a much hotter operating temperature. The people in Volkswagen knew that if I could increase this number, right, you can make that a hotter number, then the efficiency is going to be much bigger, which means essentially it translates to better gas mileage. And that's why, well, that's one of the reasons the Beetle was a huge success in the late 1960s, early 1970s, is because of the efficiency, right? You were talking about American cars which were getting 12 miles per gallon, maybe 15 on the average. And you're talking about the Beetle getting close to 30, right? You're more than doubling, or possibly about doubling, your efficiency by increasing this number. Now, it turns out that there were some offshoots to that, including the emission of a lot more nitrous oxide, which wasn't foreseen right at that point, but did become the nitrous oxide is a precursor to the formation of smog. And if you live, or if you heard about the air quality in the LA basin in the late 60s and early 70s, it was pretty bad. And smog was one reason as why. Anyways, there you go. There's a little bit of history on the understanding of this cycle. Okay, so a couple of theorems about what's going on with the heat engine, and what we'll do here is try to do a quick example to calculate what this looks like, how does this connection get made? How do we recognize what's going on here as what's going on here? How do we put these things together? So let me do that example here for you. I'm gonna just kind of erase this a little bit. Here's what we want to do. I want to take a fairly simple cycle, and take a look at where is the heat going? How are we getting the work out? In other words, how do we recognize this whole thing on a PV graph? Right. So let's suppose that I'm going to do a fairly straightforward cycle. I'm going to do a cycle that goes up here, drops. So let's suppose this is 1, or maybe this is, call this A. How about AB? And drop this down here, and this will be C. And we'll reconnect here, and it's going to go 1, 2, and 3, like so. All right, this is a fairly simple cycle, but it is going to be reversible. And I'm going to assume that we are doing this so slowly as to have a reversible process on each one of those. Now you'll recognize this as an isovolumetric, you'll recognize this as the isobaric, but what's the other one? It's an adiabatic, let's say. Let's suppose this is adiabatic. All right, and I've got some volumes and I've got some pressures. P, well, I gotta erase that, and then, or I could just go P, B, and PA, like so. Oh, but I haven't labeled my X's. All right, there's P all the way up the top. All right, let's suppose that we know a couple of these volumes and pressures. We're going to need to find some of them. But ultimately, the first thing I want to do is just say, this is a heat engine cycle. And you can tell that because there's area. And the area translates to the work done by the cycle, which means that all of this in here is work done by this cycle. That's how I denote that there's work coming out, right? There is work done by the motor, by the engine during this process. Is there work done here? Yes, I had to do that work. I was the one who added that work. There was no work done here, so that's not a big deal. So ultimately, the net amount of work put out by this process is this shaded area in the cycle. That's basically always true, okay? What about QH? Where is QH on this graph, on this, with these set of processes? Well, let's look at it, right? Here I am starting at a particular volume. I'm going to hold the volume fixed, okay? So imagine I've got a cylinder, right? Here I am at A, and I've got my cylinder and piston here. Remember how this happens? The gas is in here, and I'm telling you that that volume does not change, A to B. So I have fixed this. I'm going to put two little prongs on there. I don't know if they really come out too well, but however you want to do this, I'm going to fix this here. I'm going to lock that piston in place, and I'm not going to let it move. How am I going to increase the pressure such a big difference here? How am I going to increase the pressure to such a high value? If I can't move this thing, then I can't compress it. Therefore, since there's only two ways to increase you'll notice that that increase in pressure is tantamount to an increase in the internal energy of the gas. How am I going to increase that energy? Well, I could do work on it. No, I can't do work on it. The first law allows says, yeah, that's a way to do it. But I'm saying, no, I'm not going to do that in this case. So how do I get the pressure to be so high? I must be heating it. Okay. Therefore, from A to B, there is heat going in. I'm adding heat to it. That's where QH is. So if I think about where am I drawing QH from, that's this process right here. QH is going in right here. That's QH. Let me make that a little bit more easy to see. let's write that a little bit more visibly. QH is going in during the isovolumetric heating process. That's a heating process. That's where this is going in. All right, what's going on here from C to A? Well, basically by process of elimination, you can imagine this is adiabatic, so there's going to be no heat transferred here. And therefore, this must be the QC part, but let's try and reason it out before we do that. The QC must be heat that is leaving the system, right? And now think about what's going on here. I'm at a a large volume and I'm going back to a small volume. So basically I'm compressing my cylinder, right? So this would be, for example, A to B. If I'm thinking of going from C to A with my piston and cylinder device here, I'm at C and I've got a large volume. And I'm going to A as my final state. I'm going to compress this thing because the volume is dropping, but I want to keep it at constant pressure, isobaric, right? That's the C to A process. If I compress this thing and I don't let anything else happen, then I'm going to crank the volume. I'm going to crank the pressure way up, right? If I compress it but I let nothing else happen, the pressure will spike. So I don't want that to happen. I want to be able to compress it, but then remove some energy such that the pressure stays constant. And if you think about your isotherms, C is at a much greater isotherm than A. So you know that the temperature is dropping, and therefore the internal energy is dropping, which means that while I am doing work on this thing to compress it, I must be transferring much more energy away, and that must mean I have a large heat out transfer, and that's your QC right here. That means I've got this thing on ice cubes, right? There's ice cubes here. All right, and so heat is leaving, and that's going to be your QC part. That's right there, coming out is QC. That kind of reasoning is what connects this type of diagram with the PV graphs. Where am I putting the heat in? Where am I taking the heat out? Where's my net work? You should be able to recognize all three of these quantities on one of those plots, and that's how you do it. Now let's go through and take a closer look and see if we can calculate some things like what are these heats, what are these works, and therefore what is the efficiency. In order to do that, I'm going to have to assume a few numbers. Therefore, let me put a few numbers into this graph here, and we will go from there. Let's suppose that this volume here is 10 to the minus 3 cubic meters. And let's suppose that this pressure up here, pressure B, is 10 atmospheres. This means that I would need to know how many pascals there are in an atmosphere, because I can't work in atmospheres. Maybe you can, I cannot, because I don't want to, I don't like to, and I don't know any of the numbers. I know how to work in pascals though. This means that the conversion that we require is the conversion from how many atmospheres there are into how many pascals there are, and it turns out that there are 101,000. Typically, it's for our purposes, it's basically 10 to the 5th. If you want to, I just know it's 101 times 10 to the 3, 101 kPAs. Now remember, if you haven't seen the Pascal before, remember that's an amount of force per square meter. That's an amount of force per square meter. So that's a pressure. Okay, so with that, let's start. And let's start by looking at what the gas must be in order to have this happen. Now, in order to analyze an adiabatic, you know that I need to know the gamma, which means I need to know what kind of gas it is. So let's suppose that I've got 1 mole of monatomic ideal gas. When you see that, it's a tick in your mind to let you know monatomic ideal gas, what we talked about last time. This tells us what the gamma factor is, and that ultimately is what is involved in analyzing a an adiabatic. So when you see that, remember that you know that gamma is 5/3. Okay, let's go in and try to see if we can figure out a few things. For example, if I want to basically figure out what these heat transfers are, how much work there was, I'm going to first need to know everything about the cycle. That means I need to know what the volumes at A, B, and C are, and I need to know what the pressures at A, B, and C are. Now, because it's an ideal gas, I can then find what the temperatures at A, B, and C are. All right? So we know what the volume is here. I know that this is 8 times the original volume, so we've got the volume at both of the points. I know what the pressure is up here, but I don't know what the pressure is at A and C, and therefore I'm going to need to figure that out before I can calculate anything. All right? Therefore, if my first task for part A in this problem is find how much heat was added to the cycle, I can't even do that until I find out all of the state variables at A, B, and C. So let's go find the pressure at state C, because I'm going to connect the adiabatic to point B here. And therefore, when I find the pressure at C, we know it's the same as the pressure at A. All right, so let's now find, actually I'm going to have to erase all of this, which is too bad because I really liked this drawing. Okay, so now let's find pressure at C, which, by the way, is equal to the pressure at A. We're going to utilize the adiabatic that connects B to C, which tells me that PV to the gamma at point B should equal PV to the gamma at point C. Since we know what gamma is, we know what the pressure at B is, and we know the ratio of the volumes, we should be good to go on finding what the pressure at point C is. Pressure at C is therefore going to equal the pressure at B. But I'm going to need to swing this volume underneath here and know that the volume B divided by the volume C, that thing to the gamma, is how I'm going to calculate the pressure at C. Since we know what that is, B to C, that's 1/8. Right, because it's VB first. Yeah, so it's VB going to VC, so this is 1/8. And pressure at B initially was 10 atmospheres. This is 10 atmospheres multiplied by 1/8. But that 1/8 is to the gamma, so this is to the 5/3. Like so. All right, remembering that this thing here, if I've got 1 atmosphere being that, then 10 atmospheres is just this number times 10 to the 4th. Okay, so I can put that in here instead of atmospheres, and I'll be copacetic with the units. Dealing with 1/8 to the 5/3, multiplying this, and that's going to come out to be a particular number. And that number, let's see, that number turns out to be about 3.2 times 10 to the 4th pascals. Let's see, is that right? Yeah. It's a little bit less than 3.2, but I'll just round it off. Alrighty? Okay, checkpoint on pressure at C. That's the same as pressure at A, so we should be all good to go in terms of state variables. And should I need to, I can now always utilize the equation of state for the ideal gas and go find all the temperatures at A, B, and C. I am not going to do that, however, because ultimately what I want to do now is go find what is this heat. What's the heat that it took to go from A to B? Happy days. Now look, remember, we've talked about how to add heat at constant volume. And that's what this is. It's a constant volume heating process. Therefore, this is a sensible heat. And QH should equal N times the molar specific heat at constant volume times the change in temperature. Right? This is exactly the equivalent of MC delta T, but it's utilized to be molar, all right? And it's done at fixed volume. Remember how to calculate these things if it's a monatomic ideal gas. If it's a monatomic ideal gas, I count my modes available to hold energy. 1, 2, 3. 3/2 R. And at this point you would say, oh no, I don't know what the temperature difference is. That's okay, I'm not going to calculate it. You're welcome to, but I'm going to take that and I'm going to use this instead. If I delta this T, I delta the left side. I could delta this thing here, and that would be equivalent to a delta in the T here. NR delta T is the same thing as delta in PV. Therefore, I can write it this way. Right? The 3/2 has to come with me, but NR delta T, that would be, I can't fit my delta in here, but you can imagine it's delta of that side. And the only thing that I have that could possibly be changing on the right side here is the time. Good one. Temperature. All I have to do now is take P and V at point B and subtract it from P times V at point A. Multiply that thing by 3/2, and we're rolling. Okay. All right, since volume at B and volume at A are exactly the same, all this really comes down to is the pressure difference. And since I know the pressure at A and I know the pressure at B, all it is the difference in those pressures multiplied by the volume. Let's see, if you're keeping score at home, when I do that, I get a number that is about, let's see here, QH. So QH, I find to be about 14, I'm just going to say about 1,500 joules. All right, somewhere around there. Okay, if I'm now interested in the exhaust heat, okay, the exhaust heat, what's QC? Well, just as we did Q for the constant volume, notice that this Q is a constant pressure, and therefore this will be N times Cp delta T, right? Everything's kind of coming together, right for the analysis of these things. This is exactly what we've been developing, all the tools to go start attacking things like this. This is a constant pressure process. Again, I'm going to look at this and say, I have a monatomic ideal gas. I know what Cp is. It must be 5/2 R, which changes this into a 5/2 NR delta T. And if I pull the same trick as I did down there, all I got to worry about is the P and V, and I don't need to calculate what the actual T is. Okay, so this is going to be 5/2 of PV evaluated at final, which is A, minus PV, which is evaluated at C, which is the initial. Okay, if I calculate that number, it turns out to be approximately, what did I have here? About minus 550 joules. Okay, negative makes sense. It's heat coming out. Yeah. This was positive, makes sense. It was heat going in. The difference between these, let's talk about that. I started off this whole thing by saying the net work done is the area underneath this, I'm sorry, the area in this shaded curve here, in this shaded region. We could certainly do an integration down the adiabatic and then subtract off the work done by the isobaric. But don't you think there's a better way to do it? Feels like there should be, because ultimately I put energy into this, I'm exhausting energy out of it, and I'm getting work done by the cycle. Now remember, the cycle suffers no change in the internal energy. And I mentioned this last time. Since this is a cycle, there's no change in energy. A back to A. Internal energy change, 0. Therefore, the heat added must equal the work done. And you can translate that to mean if I take that and I add this, that should be my work done. Right? It's just, that's first law reasoning. It's energy conservation. The heat that I put in should be the work that I get out, because the gas itself does not change its state, cycle to cycle. Therefore, work done by this cycle should be equal to, I don't know if I necessarily want to say minus, because I've already got the minus in here. So I am going to say minus, and I'm going to put this in absolute value bars like that, because I love this negative sign here. I want to see that negative sign. That's just me. If you don't want to put it there, that's fine, but just don't screw it up. You need to make sure that it's basically this number minus that number. How much went in, how much came out, right? This negative only tells you it's leaving, right? So this should be 1500 minus 550. Which, unless I'm very much mistaken, is 950 joules. And that's the work done by the cycle. Now, again, if I'm being extremely careful with my signs, if I'm being really careful with the signs, and I go back to this thing, I should be able to write that hold on, I go back to this thing here. I said this thing, but I didn't actually point to anything particular, so if I just think about first law energy conservation for the cycle, I think you can see that QH comes in and should equal QC leaving and work leaving. Right, just from an energy conservation standpoint. Therefore, if I'm interested in the work, it really should be the difference between the heats. And this already takes into account the direction of the energy flow. Okay? In other words, I've already seen this heat's coming in, that one's leaving, and that work is leaving. I've already taken that all into account. So by the time I get to analysis of something like this, I only need to work with magnitudes, because I already know the work is done by the cycle, and that's work that I get. So if I was being really careful with the signs, this technically should be negative 950, but that negative 950 is already taken care of when I did this first law analysis right here. Okay, so the work done is 950 joules. That's the work that was done by the cycle. Let's take a look at the efficiency of this cycle. This is a fun one, because we have not discussed efficiency as of this point. And it's a very, very useful thing. It's a useful quantity to have at your fingertips, because it's a quick and easy way to figure out how efficient something is. I think I got taught it in this form when I was taking an engineering thermal class so many years ago. Whoops. And I already screwed it up. It's always what I come back to. How efficient is something? It's what you get out divided by what you put in. Right? It's what you're getting out. What are you getting out? What's useful that you're getting out from here? Work. Okay? For a heat engine, that means the efficiency should be the work that's coming out. What did I have to put in order to get work to be done by this cycle? It has to be the QH. That's the heat transfer that even started the whole thing. So this has to be W over QH. That's the efficiency of a heat engine. We can calculate that really quickly right here. That's going to end up being 950 divided by 1500. You'll notice that the units are going to go away, which they should. The efficiency is simply a number. It's a ratio describing how much of what you're putting in is going into what you want. Okay? And this is going to be a number, I don't know, on the order of about 60% or so. It's going to be a little bit better than 60%. It's going to be about, say...
It's 63.
Oh, is it 63? Perfect, 63. About 60, it's 0.63, which is going to come out at 63%. I will do this appropriately then, because I said it was 0.63, so it's going to come out to be 0.63. All right. So for every 1 joule of energy I transfer via QH, dumping into here, I get out 0.63 joules of useful work. This, by the way, is fantastic. If this was what we could get, this would be great. Typical efficiencies of the more common things that we call heat engines in this case, such as the first thing that comes to my mind, the engine in the car. The engine in the car, if it's a gas engine, I mean, you're hoping for about 25%. It's usually on the order of about 20%. In other words, for every amount of gasoline, for every amount, or say, a volume of gasoline that you put in, a unit volume of gasoline, it's a particular amount of energy in that unit amount of gasoline. You're throwing away 80% of that useful energy, and you're using 20% of it to drive the car. So that's part of the reason that all of this got thought about in the 60s and early 70s, because we realized that there was a slight problem with that. Ultimately, engine efficiencies have gotten slightly better, but they have not gotten very much better until the advent of the hybrid and the electric car. Now, electric motors can run 80% efficient. All right, sometimes 90% efficient. And that's just the facts. So even our bodies are essentially heat engines, right? If you think about the application of a cycle like this to us, I mean, that's more or less kind of what we're doing. We're putting heat in the form of food. We're exhausting a lot of heat, and we're doing usable work. Like here I am doing usable work. This is what I do for you people right here is my usable work. I am, however, also only about 20 to 25% efficient. If I could get up to 60% efficient, wow, think about how amazing that would be. All right, so this idea of efficiency, really useful. I keep a little stamp on that one because ultimately it's vague enough to be actually extremely useful as long as you can apply it to the situation you have. All right. So this is a little bit more on how the heat engines kind of come together with all the analysis that we've done with the ideal gas, the molar specific heats, and all of these thermodynamic processes. I want to now introduce one more thing, and that is I want to look at, okay, let's suppose that we consider the most ideal engine possible. Okay, so what would be the efficiency of the most ideal possible engine? The most efficient possible engine is certainly the reversible one, of course, right? Which we did assume in this case. It's known as the Carnot engine. Okay, the most efficient engine is known as the Carnot engine. How do you calculate the efficiency of the Carnot engine? Well, we go back to this for a heat engine. We go back to looking at what the work is compared to the heat input. The work done, as we've seen here, can actually be written as a difference in heats. If I apply that to this, you'll notice that I can simplify the efficiency expression. Like so. Now, there's nothing so far that has told us that we are at a Carnot engine. This is just the definition of the efficiency and a little bit of first law energy conservation. What is it that's going to get us to the Carnot engine? All right. The Carnot engine is the one in which not only everything is reversible, but you are running it at in such a careful and thoughtful way that there's no extra losses brought in. All right. So what I want to do here is bring in another quantity which describes how we can mathematically consider describing basically energy losses. This is a way of thinking that is going to be possibly somewhat new, but as you think about it, it will become very powerful, and that's how thermodynamics essentially becomes such a wide-ranging applicable subject. The Carnot engine is the one that is run with no possibility of any loss, right? No losses at all. It's a completely idealized reversible engine. No losses. In other words, when I say no losses, I'm saying there's, if you consider a normal car engine, right, what goes on in there is a complete disaster. If you consider what happens inside a cylinder in your car's engine, if you have one, the cylinder is such that, so for example, the cylinder is, say, filled with air that gets drawn in when the piston goes down. As the piston comes up, it compresses all of that. The little injector at the top, if you have a normal gasoline engine, shoots in a little bit of fuel, and at that point, the thing explodes, right? Because there's a little spark plug in there, and it goes, bzz, and the whole thing goes, and that bang drives the piston down. In other words, it does work on the piston, pushing it downwards. But this is a disaster of a situation when it comes to trying to describe it in a realistic sense, because there's nothing ideal or reversible about any of that. What we want to think about is the one where there's no friction between the walls of the cylinder and the piston. There's no losses in a sudden conflagration of combustion, right? There's no losses of noise, vibration, right? We just throw all that away. We're looking for the best possible situation because everything else is going to be less than that. We found the ceiling. Okay. The way we describe this idea is with the concept of what's known as a new variable known as the entropy. Okay, this is a state variable, just like energy, pressure, volume, temperature. They are all state variables described. I erased my thing here, but I would have an entropy at A, B, and C. Okay. And what we find is that if you operate something at the best possible level, right? In other words, you have eliminated all possibility of losses due to friction or turbulence or noise or vibration or whatever. What you find is that when you go around this thing, right, you sum up all of the heats transferred divided by the temperatures at which they transferred, that it's equal to 0. This was what Clausius found. And he actually described it mathematically in a way that looked like this. All right, that's due to Clausius. In other words, the path integral around the processes, like, right, A to B, B, or no, A to B, B to C, C to A would be your line integral here, and it's closed, so it goes all the way back to where it started. And you're thinking about how much heat you added at what temperatures, okay? When you do that, what happens is you can say that, for example, the QH that I added divided by the temperature it was added at would be equal to the QC divided by the TC. What temperature was that added at? Okay. Now, if you fool around with this type of expression, you can come out with an idea that if I, for example, flip-flop these two things here, you can come out with the idea that QC over QH is a certain ratio, right? How much, it gives you the percentage of exhaust heat, right? How much did you exhaust from your system? But that is related to, if I flip-flop these two things, that's related to the temperature at which I'm pulling those heats. Okay, because remember, ultimately, these are the heats of reservoirs, right? And so these reservoirs are not changing temperature, but if I know what temperature I have, what are my operating temperatures of the cycle, then I can get a ratio of those temperatures to be equal. It will find out to be the same as the ratio of the heats that I'm transferring in and out. And therefore, the Carnot efficiency actually ends up looking like swapping out that ratio of heats. The Carnot efficiency is special because we're going to denote it with the C down here as being 1 minus TC over TH. And this is the point where you can reach the conclusion that with a higher and higher TC, the efficiency gets worse and worse. Remember theorem number 3 that I wrote for you over there? When TC gets higher and higher and higher, that kills the efficiency. Why? Because it's getting closer and closer to TH. And that means this fraction is becoming closer to 1, and therefore the efficiency is getting closer to 0. This is one reason that you can kind of mathematically see that theorem. It's in action right in here. The opposite is also true, right? I could lower TC, and that would cause this fraction to become smaller, and therefore the overall efficiency would be larger. Now, what I was telling you about the Volkswagen Beetle is that they didn't do that because for gasoline engines, TC is basically the atmospheric temperature, and we're not changing that. Okay, we are, but at that point we were not changing it significantly, and so TH was the thing they concentrated on increasing. So they made this number a lot bigger, which caused the overall decrease of the fraction and therefore the increase in the efficiency. Okay. So let's ask an interesting quick offshoot question here. Which one is it better to do? Is it better to decrease the cold temperature, or is it better to increase the hot temperature? Is one of them going to give you a bigger increase in the efficiency than the other? Let's take a quick look and do a bit of fun math here on this one. Let's suppose that I'm going to decrease the operating temperature of the cold reservoir here. Let's suppose that I'm going to take TC and I'm going to let it become Tc minus a little bit. Okay, I'm going to get Tc minus a little bit, which means I should be overall increasing the efficiency of this, right? Because this is getting lower, and therefore 1 minus a lower number is a bigger number. So I should be increasing the efficiency. Let's see what happens. I'm going to get 1 minus Tc minus delta, whole thing divided by Th. Right? But that means I'm going to factor this negative sign through here, and that's going to become a positive. So really, it's going to end up modifying the expression to becoming what it was before, plus delta over Th. So there's a slight increase in the efficiency by this number right here. That's an increase in the efficiency, as you'd expect. Now let's look at the other situation. I'm going to take Th, instead of decreasing the cold temperature, I'm going to increase the hot temperature. Now suppose I'm going to go delta of an increase to the hot temperature. Okay? If I do that, now the Carnot efficiency becomes 1 minus Tc over Th plus delta, like so. Now I'm assuming delta is a fairly small number. So what I'm going to do is factor it out and cause the lower expression to look like that. If I do that, what I'm going to get here is that basically I am multiplying the fraction by this set in the parentheses to the -1 power. Right? I don't know if you can quite see that, but that's a -1 there because I flipped it over, -1. Now I can use the binomial approximation on this because ultimately delta should be a small increase compared to the hot temperature. So this should be approximately the same thing as 1 minus Tc over Th multiplied by 1 minus delta over Th. Okay, if I'm approximating this, then 1 plus a small number becomes 1 minus a small number when the power is negative. Okay, so if I now factor this through, it becomes Tc over Th with the 1. And I'm going to multiply this thing by that, and it becomes positive Tc over Th times delta over Th. So lo and behold, indeed, I get another increase in the efficiency from the plus sign with this ratio here, but it's knocked down a little bit by this thing. That actually ends up lowering the total amount that I'm adding to the efficiency compared to when I did it with the cold temperature. Therefore, this is the most efficient thing to increase your efficiency. How about that? We're being efficient about efficiency. Isn't that great? That's the whole thing about today's world of energy is efficiency. And not only that, we're even being efficient about the efficiency. All right, so let's go back and think about the entropy here. The entropy's definition, we're going to use the symbol capital S for the entropy. Now, the entropy itself is typically not a useful quantity, but the change of it is. Therefore, when I think of the change in S, that's what we're talking about when we do this dq over t. Now, for example, if this is a process that is isothermal, okay, if this is isothermal, then my temperature can hop out of the integration here. And really all I get is an integral of dq. Okay, so if I think for isothermal, I can come up with a really quick and easy way of figuring out what the change in the entropy is between two isothermal points. It would just be q over t, integral dq. since the temperature remains constant, it's whatever that temperature is, and this will end up being how much heat are you adding or subtracting from the process running up and down the isotherm, right? You would also note that this heat here is going to equal the work done during an ideal gas process. Because the delta T is 0 for an ideal gas, that means the delta E internal is 0. And so by the first law, this Q is equal to the W when you think about an ideal gas isothermal process. What would probably be a useful thing to do here, although I think we're running just about out of time here. So what we'll do is next class we'll come in and take a slightly closer look at what changes the entropy and what ultimately the entropy is telling us. Okay? I was kind of framing it in the situation that we're talking about no losses, which means that the entropy change around a Carnot cycle should be 0. And if you've heard of the word entropy before, if you've thought about what it's telling you, then possibly you will know that the entropy is essentially a measure of how disordered the energy is. Right? So an increase in the entropy means the energy is less useful for coming out as work. Right? It's more random and disordered. We need pretty good energy in order to be work. But if the entropy is increasing, we're not getting that. Okay, so that's why the Carnot cycle has an entropy increase of 0 all the way around it. The gas is completely in the same exact state as it was. There's nothing added or subtracted to the energy quality, and therefore we can get as much work out as possible. Okay. I will leave you today with the idea that there is no possible way to get the efficiency of any cycle to be 100%, because the way you would do that is by causing TC to be 0. And we talked about that initially as a consequence of the third law of thermodynamics, in which we cannot actually reach absolute 0 on the Kelvin scale, which is what this would be if you wanted a 100% efficient cycle. Therefore, we cannot have those. And thus, life goes on, and in an imperfect and ultimately inefficient way. And with that thought, I will see you tomorrow, or / in the next video. Ciao for now, folks.